We begin with 12.1, which discusses numbers and sets. All right. So one of the most basic understandings that we need to have of algebra and numbers is number sets in general. Numbers are so infinitesimal that we need to group them into what we call sets on a technical term, but on a more basic term, we would call them just groups of numbers. One of the easier ones to understand would be positive integers. So the symbol for positive integers is usually described as a Z symbol, as you can see on screen, and it represents positive integers. Positive integers are whole numbers that are positive, including numbers 1, 2, 3, 4, 5, etc., but not necessarily in that order. As long as it's positive and a whole number, it belongs within the set of positive integers. Now, positive integers are not the only groups of numbers out there. We also have rational numbers, something that students have difficulty with. It's usually denoted with a Q symbol and a dash throughout it, like so, and is described as a ratio of two integers. So any number that can be described as a ratio of two integers fits within this set. Let's actually move it over here and give it a proper title. So we'll call this here rational numbers. Now, examples here would include 4 over 3, 7 over 1, 19 over 4. The list goes on and on. As a quick example, the number 10 is a rational number, even though it doesn't appear as a ratio of two integers. The reason why it's a rational number is because it can be described as 10 over 1, 20 over 2, and so on and so forth. However, a number like pi is not a rational number. The reason being is that pi cannot be described as a ratio of two integers. In fact, pi is an infinitely recurring decimal value. And the trick part is that the decimal continues forever with a pattern that continuously changes, as in it doesn't have a set pattern. All right. This brings us to imaginary numbers, the set that we actually want to focus on for this chapter. Imaginary numbers is usually described with an I letter, represents imaginary numbers. And imaginary numbers can completely consist of a square root of a negative value. You'll most commonly see it as the square root of -1 or any square root of a negative value in general. I'll pause here while we catch up on notes. If anyone has any questions, please raise your hand. Okay, this brings us to section 12.2. Imaginary numbers. As we mentioned, imaginary numbers consist of the square root of negative values, something that wouldn't exist in the set of real numbers. So an imaginary number is a number whose square is a real number that is not positive. So we have it designated as a variable already, where I represents the square root of -1, which means that I squared is equal to -1. Manipulation of imaginary numbers is a popular department of mathematics itself. Let's go over some questions relating to I as long as we have this as the main definition. Now, in this example, I'm asked to evaluate bracket 3i close bracket squared and bracket -9i close bracket squared. Then I'm consequently asked, are 3i and 9i imaginary numbers? Let's start with processing bracket 3i squared and -9i squared algebraically first. According to BEDMAS, if I want to square this becomes 3 squared times I squared. I am, of course, using the exponential rule that states that when I have two variables or two numbers multiplied, held to the same exponent, the exponent gets shared or distributed to both. In the next step, 3 squared is 9. I squared, which we already have defined up here, is going to be -1. The final answer here is -9. So the square of 3i is negative simply because I is an imaginary number. And since the square of 3i is negative, therefore, to answer the secondary part of this question, 3i is an imaginary number. So let's set that up as a statement. The square of 3i is negative. Therefore, 3i is an imaginary number. Moving on to the square of -9i, we get, using the same format, -9 squared times I squared. -9 squared is positive 81. Since the square of any negative number within brackets is always going to be positive, the square of I is equal to -1. And I end up with -81 as my final answer. So the square of -9i is a negative number, so it's an imaginary number too. So I'll set that up as my statement. And I'll pause here while we catch up on the notes. Please let me know if anyone has any questions. Moving on to my next example then. Here I'm asked to suppose a is a real number. I'm asked then if the square of ai can be positive and if ai is an imaginary number. So once again, we have I squared is equal to -1, which means if I was to square ai, I would get a squared times I squared, which becomes a squared times -1. Let me pause here. So far, I don't know whether a is positive or negative, nor do I need to. The only information I'm given is that a is a real number. Real numbers can be positive, can be negative, can be zero, they can be integers, they can be decimals, they can be fractions. Real numbers is a massive set of numbers. But regardless, as long as I'm squaring it, I know that the answer will always be positive. So a squared is a positive number, -1 we know is a negative number, therefore my final answer here becomes, even without knowing a, -a squared. So how does this tie in to my understanding? What statement can I give a question like this? Well, even without knowing what a is, because a is a real number, its square must be a non-negative real number. Therefore, the number -a squared cannot be positive. This tells us that ai is an imaginary number whenever a is a real number. So this brings us to an important theorem here then. If a is a real number, then ai is an imaginary number. Okay. So one of the main concepts within the world of imaginary numbers is the complex solution to quadratics. For example, if I had an example where x squared is equal to 25, and I wanted to solve or isolate for x, the one and only step I need to do here would be to take the square root of both sides of this equation. Most students would solve this and come to the conclusion that x must be equal to 5. Can anyone here spot the mistake with x equals 5? Yes, Dorothy, go ahead.
The other solution could also be x equals -5.
Excellent work, Dorothy. Thank you. The other solution is that x can equal to -5. You can lower your hand now, which means that we have two solutions. X is equal to positive and -5, which suggests that when we're dealing with quadratics, we need to always watch out for the possibility that the square root of any positive, especially perfect squares, is always going to be the positive and negative as a solution. 4 is a perfect square because it's made up of 2 times 2 or -2 times -2. And the examples go on and on. So the same is true for imaginary numbers. The main conundrum here would be the consideration that what if I'm dealing with x squared is equal to -1? I is a possible solution here because I is equal to the square root of -1. However, this equation, just like the one to the left, is quadratic. And most of the quadratics that we have studied will have two solutions. Does that mean that x squared equals -1 have two solutions too? let's go ahead and examine a question similar to that one. Okay, so here's our example. Find another imaginary number besides x equals I that is a solution to the equation x squared is equal to -1. One way to go about this question is to compare it to a very similar equation we already know how to solve. Like I said earlier, x squared is equal to 25, but for now, let's use a slightly different number. Let's say we'll let a squared equal to 4. We already know we have two solutions here. A is equal to +2, and a is equal to -2. If that's the case, and we know all we need to do is introduce a positive negative sign when we take the square root of both sides, then we can do the same thing for -I squared. So if we know that -I squared is equal to the same, we can set it up as -I squared is equal to, let's factor out the -1, shall we? So -1 here times I, the whole thing is squared. Which means according to the distribution of exponents, I can distribute the square to both. So that's -1 squared times I squared. -1 squared is +1, so it's redundant to include in the next step. So I only have I squared here, which is equal to -1. What that tells me is that -I is also a solution to x squared is equal to -1. Let's try that out. So therefore, -I is also a solution to x squared is equal to -1. Further reinforcing the concept that whenever we have x squared is equal to a value, whether it's the real world set of numbers or imaginary set of numbers, we can introduce a plus or minus sign, just like when we take the square root of both sides of x squared is equal to 4. Now let's try that and expand it to other examples as well. In this problem, I'm asked to find all solutions to each of the following equations. And as predicted, we have situations where we're trying to solve for negative squares. Let's try it out. Let's start off here with part A. I solve part A as if I'd be solving a normal setup. So I have here x squared is equal to -16. The first step is to take the square root of both sides, which means I will take the square root of the left and the square root of the right-hand side. The square root of the left-hand side is fairly straightforward. It's simply x. The square root of the right-hand side, since we're still a little bit new at this, is a little bit tricky. We'll get used to it over time, but for now, it makes sense to write it out as plus or minus the square root of negative 16, just to prepare ourselves for the positive and negative answer. And then the next step, I can actually process it a little bit by separating it into two factors. So that would be -1, or rather the square root of -1 times the square root of 16. Each of these are straightforward. We already know the square root of -1. Catherine, why don't you help me out with the square root of -1 here? What would it be equal to?
It would be equal to I.
Very good. You got it. Be equal to I. And the square root of 16 is equal to 4. Putting it all together, math convention states we should always write the coefficients first. So plus or minus 4i is my final answer. Thank you, Captain. Just like in part A, I'm going to solve B the exact same way, but this time I'm going to expedite the process a little bit. I start off here with x squared is equal to -24. Square rooting both sides, I get x must be equal to positive negative the square root of -24. Separating the factors, I get x must be equal to positive negative square root of -1 times the square root of 24. The issue that I'm beginning to see right away here is that 24 is not a perfect square. It's not the same as the number 4 or the number 16 or the number 25, where the square root of each of those numbers would produce a whole number. Instead, I would like to reduce the square root of 24 as much as possible. One tactic that I'm a big fan of is to write the number that I'm trying to simplify as a square root and divide it by the smallest factor that is not 1. In this case, if I'm dividing 24 by the smallest factor that isn't 1, would have to be 2. 24 divided by 2 is 12. 12 divided by 2 is 6. 6 divided by 2 is 3. And finally, the smallest factor that I can divide 3 by that isn't 1 would be 3 itself. Once I'm done with this process, I can see here on the left-hand side of the line that 2 times 2 times 2 times 3 produces 24, meaning these are all the simplest factors of 24. All I need to do from here is take every pair of factors, square rooted, which means those are the ones that can leave the square root and the rest remain, meaning that the square root of 24 can be rewritten as 2 times the square root of the remaining two factors there, which are 2 and 3, 6. I'll highlight them both for emphasis here. And that's one way to simplify the factors that I'm looking at over here. So back to my problem. X here is equal to plus or minus the square root of -1 is I. I'm going to write it on the right-hand side apprehensively. Or actually, rather, I'll leave it where it is for now. It's going to matter later on. Multiplied by 2 times root 6. A simple rearrangement here will give me a final answer. So plus or minus 2i root 6. I'll pause here while we catch up on the notes. Please let me know if anyone has any questions. Okay, this brings us to the next example slash problem here. What about when I'm dealing with higher powers of I? Powers that are much larger than squares or cubes. How do I react then? There has to be some kind of established pattern. There's not a likely chance that I'm expected to solve higher powers by hand or anything along those lines. So starting off with part A, for example, I cubed here is equal to, like any cube, the same base multiplied by itself 3 times. So that would be I times I times I. Putting 2 to I together, because I'm used to the idea that I squared is equal to -1, and I get I squared times I, in which case I have here -1 times I. So my final answer here is -I. We can use that result to find the answer for part B as well, without having to break it down into its smaller parts as well. So part B here, I to the power of 4, is simply I cubed multiplied by I. I cubed multiplied by I here leaves me with -I times I. That produces -I squared. We already know that I squared is -1, so negative of -1, double negative produces a positive, and I end up with +1. If we keep going in this format, we'll find that there is a quick pattern emerging. The pattern would be that if I have I to the power of 1, that's equal to itself, I squared is equal to -1, I cubed is equal to I to the power of 4 is equal to 1, I to the power of 5 is equal to I to the power of 6 is equal to -1, I to the power of 7 is equal to -I, and I to the power of 8 is equal to 1. Comparing this, it doesn't seem apparent at first, but I should be able to notice that the powers of I repeat in groups of 4. And that's because I to the power of 4 is equal to +1. To get the next power, we multiply this equation by I, and the cycle starts again. So all I need to do is keep that in mind, that I squared is equal to -1, and I to the power of 4 is equal to +1. I can use that to solve some of these harder questions, like the ones that we see over here in parts E, F, G, and H. For example, I can now solve part E much easier than separating it into its many factors. I to the power of 10 is equal to I to the power of 8 times I squared. I already know what I squared is, and I to the power of 8, 8 being a multiple of 4, means that it's +1. I squared is -1, so my final answer here is -1. Now I'm going to give the class a few minutes to solve F, G, and H on their own. I don't want anyone to hand anything in. That will be for the homework later on. But I'm going to allow everyone a few minutes to try these ones out. It's 8:03 right now. We'll come back at 8:08, and then I will solve these questions on the board and we can compare notes.